This is the empirical mass of magnesium sulfate hydrate lab. Objective number 1 is to be able to determine the percent by mass of water in this hydrate, and 2, more importantly, to determine the empirical formula of this hydrate. The bottom line here is we're trying to write the formula of magnesium sulfate hydrate and determine the actual stoichiometric coefficient in the chemical formula for the water. So it's magnesium sulfate, and we have to know, and we're after, how many water molecules are in that definite proportion in the hydrate. So MgSO4 question mark, how many water molecules are in this crystal in a specific ratio. So we're going to use a missing mass lab like we've done before, and I have a copper sulfate pentahydrate lab that we used, and we noticed the salt in that lab was a blue color. Here we're dealing with a white or colorless hydrate that we're going to drive off the water with heat. So the purpose of the lab again is to determine the chemical formula, the empirical formula, but using a percent by mass procedure. And these are the part of the earlier experiments that we did or were done in chemistry to determine chemical formulas. So we're going to find the missing mass, find the grams of that missing mass, in this case will be the water, compare the grams of that water to the grams of the remaining solid, the anhydrate, and then using our mole ratios, determine the chemical formula, or in this case, the coefficient of water in the crystal. Remember, this is a compound. It has a definite proportion by mass. It has a chemical formula. The amount of water molecules in the crystal are constant, assuming our hydrate is perfectly hydrated and that we have 100% pure sample. Okay, so with that, let's start our procedure. Okay, so we have our crucible tongs, we have our wire gauze, and we're going to continue, and the first thing we're going to do is mass out our empty containers. If you're using this as a virtual lab, you can pick student A or student B to get your value. So here is our value for student A's crucible. Remember, we're going to use the top as well, prevent the splattering. And I'm going to put this back here. I'll just keep this here for now. And we'll do student B. Again, pick one or the other. I'm using the middle crucible when we heat it to be the reference point. And we have the mass there. Okay? And so I know I could have kept that there. And we could have teared out the weight. I could have put the crucible on here and hit re-zero. All right, so now I'm going to add some hydrate to this. And this is magnesium sulfate, question mark, how many water molecules, or what that coefficient is. So I'm going to add some hydrate here. Okay. And please make note of that temperature. I'm sorry, of that mass. Okay. And subtracting out the what? The empty container, we will have, of course, the mass of our hydrate. I'm putting the cover slightly ajar so the water leaves, but enough of the cover on so that splattering is minimized. Okay, and same thing here. We're going to add some hydrate, and that changes the mass. And student A and B's hydrate values will be different, and that's the reason for having two samples if you're using a virtual lab. Okay. Make sure you pick what sample you're using, B or A, and I'll just, because I am a little bit OCD here with these videos, we'll do that. Okay. And of course, we're going to slightly take the top off there, move this back a little bit. Yes, I'm being a little crazy, but I'm tall. All right, so here we go, leaving my reference crucible here just to see what's going on with the crystal. We're going to crank up our heat, and we're going to do our initial heating. And of course, what we're looking to do is drive off all the water. We don't know if that's going to happen until I do what? Mass out the cool room temperature hydrates and cover, and keep reheating until that mass stays constant. Now, I don't know if the video is picking this up, but you can clearly hear the sizzling going on. Hear that sizzle? Yeah, that's the water escaping the crystal right there. So you can hear that kind of boiling or sizzling as we add heat to the hydrate. The water, which is attracted to the positive and negative ions in the crystal, are now being separated out and evaporating away. Okay, so what we're going to do next is we're going to do our first massing to, again, verify if we've driven off the heat. I don't hear the fizzing anymore. I could also visibly see the fog coming out of these openings of the crucibles. That has dissipated as well, so there's some observations that are telling me that maybe the water has completely left the hydrate and left an anhydrate. Notice my reference crucible here didn't change color. If you were with me with the copper sulfate pentahydrate lab, it did change color. And of course, the reasoning there is that this is magnesium, not copper. Copper is transitional, and you have some crystal field splitting that gives the color with transitional elements with water. So here, because magnesium is not a transitional element, no d electrons or no d orbitals that have electrons in them, therefore, or no d orbitals at all. But the point is, there's no color change associated with it, although it should look drier. Any case, let's go with A, and before we measure a crucible, we should never do so with it being hot, so we're going to take it off the heat to cool it, and we'll do the same. All right, we'll do the same with students B crucible as well. I'm going to put the hot crucible on the wire gauze because the cold chemistry bench here could possibly crack the crucible. Okay. Okay, the crucibles are cooled. And so now I'm going to mass them out. And we're going to write this mass down. So I have 33.83. For A. And I'm going to put that back on the hot plate. Whoop. And again, I'm using inside technique. And now, of course, B is now cool. I'm going to put crucible B, or student B's crucible, if we're keeping score at home. And we're going to see that the mass is 35.54. And we're going to heat one more time to verify. Possibly one more time. It could be more if the mass keeps changing on me. I have to have a way to verify all the water has been driven off. And we'll let that heat for a few minutes and then do another massing. Okay, we're going to go now and mass out our, or at least cool our crucibles first. Inside technique. Putting it down on the wire gauze so that I don't crack crucibles. Okay, let them cool for a little bit. Okay, now that they're cool, take the mass of the crucible for A. Let's see what that mass is, 33.81. Boy, that's very similar, but a little bit less. Before it was 33.83, so I don't know if I have to stop, so I'm going to guess what? Heat some more. And I'm going to now measure the crucible and cover and the hydrate here. Well, it could be an anhydrate now. And I get 35.52. It's a little bit lower than before. So I've driven off some more water, but I don't know if that is the final value. So I'm going to have to heat some more. Those numbers should stay constant. So we'll try one more heating. Okay, so let's take our crucibles and cool them before we measure them. And see if the masses have stayed constant. Let them cool for a little bit. Okay, we're going to mass out A. $33.81, and that's the same as our second heating. So we have verified that all the water has been driven off from crucible A. And that's all the data you need to finish that lab and determine for student A all of the moles of water in the empirical formula, or the coefficient. Okay, this one is 35.50. Well, this one is not the same, so I'm going to have to heat some more. So student B is going to have to continue to be heated. I might have had more what? Hydrate in this one. Let's move this one here. Give that a couple minutes. If you're student A, or have crucible A, then you are all set and you may begin calculating the amount of moles of water in the empirical formula of magnesium sulfate. Okay, let's see if this will be our final massing from sample B. Let that cool first. Okay. And what do we have here? 35.49. And let's heat one more time. And let's cool it one more time. Let that cool before I mass it out. Now that it's cool, I got 35.50, so 35.49, 35.50. That's confirming for me that I'm at the lowest weight. Okay, that last number on the scale is its guess. Now it's 35.49. So I've confirmed that I'm staying constant. And I'm going to stop the experiment here. And you have all the data you need to continue on with this experiment. Good luck.